The objective of this study is to fabricate and characterize flexible and natural nanoscale memory devices based on starch as a candidate for use in bio-inspired electroactive polymer materials. We also compare the resistive switching properties of ReRAM devices based on starch and starch chitosan composite. The progressive set and reset characteristic of starch chitosan-based biomemristors makes it a potential candidate for analog-based synaptic devices. 29,32. Experimental Section 2.1. Materials and device fabrication. ReRAM devices with an IM structure of O/starch/Ito and O/starch-chitosan/Ito were fabricated on a PET flexible substrate. The PET substrates were cleaned ultrasonically using acetone, to propanol, and distilled water for 15 minutes, then dried using N2-gas. The cleaned substrates then treated using UV ozone cleaner, JSE, Korea, to achieve high coverage of biopolymers on Ito surface with uniformity. Starch solution was synthesized using 4% potato starch powder, Sigma Aldrich, in dewater with 86 to 89% glycerol solution as plasticizer and filler 31 at ambient temperature and constant stirring for 1H chitosan with a medium molecular weight, decetylation degree 75 to 85%, Sigma Aldrich, derived from crab shells was dissolved, 1 weight/D. In 1% D:/D acetic acid solution in distilled water, and then mixed overnight under ambient temperature and constant stirring at 120 rpm. Both of the solutions were filtered through 0.4 mpdf searing filters. Starch solution was mixed with the chitosan solution at 1:1 D:/D, then the resulting solution was filtered through a 0.2 mp filters. The starch-based solution or the mixed solution of starch and chitosan were spin-coated on the transparent unflexible substrate at 500 rpm for 5S, then at 1200 rpm for 40S. The films were dried at ambient temperature overnight and then thermally annealed at 60 degrees C in a vacuum oven to form starch and starch chitosan resistive switching layers with a thickness of 100 and 259 mm, figure S1. Soon after the thin films had been annealed, electrodes were patterned using thermal evaporation to make ReRAM devices with a 100 N diameter. 2.2. Characterization. 1. Electrical characterizations. Electrical characteristics of the fabricated devices were analyzed at atmospheric pressure and ambient temperature using a semiconductor parameter analyzer, Keithley 4200 SCs. USA, to apply voltage and to measure current. In a typical test configuration, the samples were placed in a probe station, and bias voltages were applied to O electrode while the Ito electrode was grounded. The measurements were performed with forward and backward voltage sweeps from +3V to 4 at 0.05V/step. 2. Electrochemical characterizations. The redox properties of the SBD were measured using a POSTECH Gamma instruments, reference 3000, USA. Cyclic voltammetry, CV, curves were obtained with a point sheet as a counter electrode and a/equal reference electrode, with the desired thin film on an Ito-coated PET as the working electrode. The supporting electrolyte was 0.01 M-phosphate buffer solution. The thin film was protected using Niloufar to keep the SB thin film from dissolving during the CV measurement. 3. Optical characterizations. Akari 100 UV via spectrophotometer, Agilent Technologies, CA, USA, equipped with a transmittance accessory was used to record the optical spectrum of the samples over the wavelength range of 200-800 nm. The transmittance spectra were collected from starch-based and starch chitosan mixed thin films on the transparent Ito-coated substrate. 3. Results and discussion. Memory devices that starch or starch chitosan mixture as resistive switchable materials were fabricated on indium tin oxide, Ito right parenthesis -coated polyethylene or ethylene PET right parenthesis flexible substrates. O/starch thin film /Ito/PET and O/starch chitosan composite thin film /Ito/PET structures were used to demonstrate the memory devices with a metal/insulator/metal-ion structure, figure 1a. The devices can be wrapped around a glass rod with 2.5 mm diameter, figure 1b. They are highly transparent, figure 1b. Inset, due to transparency of chitosan and starch solutions. Potato-derived starch with a combined structure of amylose and amylopectin, figure 1c, was used as the resistive switching layer in the devices. Electrical characterizations of starch-based and starch chitosan-based ReRAMs were demonstrated under ambient conditions. In both devices, the measured current voltage, i.e., curves indicate typical non-volatile resistive switching, RS, behavior, figure 2a. During measurement of AV responses of the O/starch/eto/PET and O/starch chitosan/eto/PET devices, DC bias voltages were swept on O-top electrodes in the sequence 0E3V0E -4V0E at 0.05V/step while the ETO bottom electrode was grounded. In the starch-based device, during the first voltage sweep a positive bias from 0V to set voltage F set tilde 0.9V drove the resistance state of the memory device from its pristine high resistance state, hours, to a low resistance state, hours. This is the double quote set double quote transition. Subsequent application of a voltage of opposite polarity changed the resistance state from hours to hours, reset, figure 2a. The device can be toggled repeatedly between hours and hours by changing the applied bias polarity. The electrical characteristics of the starch chitosan-based device were examined using the same voltage sweep and measurement method. In contrast to the starch-based device without chitosan, both the set and reset processes were gradual, figure 2b. Upon sweeping an external voltage from 0 to 3V, the resistance changed gradually from hours to hours, and the hours was retained until an opposite voltage was applied, figure 2b. The polarity of the bipolar switching cycle is influenced by several parameters, such as electrode materials and work functions. By using different metals for the two electrodes of M-ion structure, the polarity of the switching process can be changed. 34 bipolar memory devices. The device remains at hours until a voltage with opposite polarity is applied which changes the device state from hours to hours, figure 2a. Figure 1. Schematic.
Figure 1. Schematic illustration of fabricated flexible resistive switching devices. A flexible ReRAM with an O/starch, PET and O/starch minus Chitosan, PET configuration. B. A magnified optical image of the memory arrays on a flexible substrate. The device is wrapped around a glass rod with a 2.5 mm diameter. Chemical formula of starch combined with amylose, C, and of amylopectin, D, as the resistive switching layer in ReRAM memory device.